Hi everyone, I am going to present a scenario that may account for the post-main sequence evolution of solar-like stars. When a low mass star leaves the main sequence, its core experiences a gravitational contraction and spins up. Recently, Spada et al. Showed that enforcing a quasi-solid rotation during 1 gigayear after the end of the main sequence enabled to reproduce the rotation rate of subgiant as measured by asteroseismology. Also obtained by Egenberger et al., these results benefited from an observational support provided by Dehavet et al., who measured a near-solid rotation in two young subgiants. Interestingly, asteroseismic measurements shows that the efficiency of the angular momentum transport seems to decrease up to the tip of the red giant branch before increasing again. This suggests a scenario broken down into several key phases that we propose to explain by the presence of a large-scale magnetic field buried in the radiative interior of these post-main sequence stars. For this, we performed the axisymmetric numerical simulation of a spherical shell filled with a stably stratified flow embedded in a large-scale quadrupolar magnetic field as represented here. This flow is subject to a radial velocity field mimicking the contraction of the core, and the magnetic field is assumed to be the product of a core dynamo during the main sequence. After one contraction timescale, the configuration is characterized by two magnetically decoupled regions. In the first one, a quasi-solid rotation is maintained by the large-scale magnetic field. In the second one, so-called the dead zone, a significant level of differential rotation exists and results from a balance between the inward angular momentum transport by the contraction with an angular momentum redistribution process. After this time, the shear built at the interface between the two magnetically decoupled regions is strong enough to trigger an axisymmetric instability. We argue that this instability is of magnetorotational type for several reasons. This panel displays the structure of the unstable mode in color with the shear in black. We can observe that the perturbation grows where the shear is negative in the northern hemisphere and positive in the south. Because of the stable stratification, these perturbations are radially confined and develop preferentially in the latitudinal direction. As displayed in this panel, they grow exponentially over time, and we can show that the associated growth rates are proportional to the shear. Finally, we find that the poloidal field has a stabilizing effect. However, we also find that the toroidal field is stabilizing. In addition, the unstable mode exhibits a non-stationary character, illustrated by the following oscillation over time in this panel. Finally, there is a fast drift modifying the phase dependency between the perturbed fields. So, all these features tend to show that the instability is a helical magnetorotational instability. After the exponential growth phase, the evolution becomes nonlinear and the instability saturates. The first two panels here display in color the normalized rotation rate and the normalized norm of the poloidal field, with the streamline of the meridional circulation and the poloidal field line in black. We can observe that the instability proceeds via a multicellular meridional circulation, which advects and mixes the poloidal field. This process creates small scale on which the magnetic diffusion can efficiently act to dissipate the poloidal field, as we can observe in this panel. As a result, the Lorentz force between the two dead zones here and here is no longer active and the differential rotation sets here. So, to account for the rotation rates of post-main sequence stars, we propose the following scenario. During approximately one contraction timescale, compatible with the 1 gigayear found by Spada et al., a large-scale magnetic field maintains a quasi-solid rotation state in the core of subgiants. During this period, the differential rotation builds up in the dead zone, and, after approximately one contraction timescale, the shear built in the dead zone is strong enough to trigger an axisymmetric instability. This instability advects the poloidal field and destroys the large-scale structure of the magnetic field. Then, the contraction accelerates the core again and produces a significant level of differential rotation as required by asteroseismology. Finally, at later stages, other processes of angular momentum transport must be invoked to explain the observed rotation rates. So, this is the end of my talk, and thank you for listening.